Hello everyone. Uh, I am Ashutosh, and I will be presenting some uh, previous state of art on particle filtering based statistical inference for positioning and tracking applications. So, okay, so we have uh, nowadays we have many robotic applications where we need to keep track of a moving robot, or we have autonomous vehicles, or we have autonomous UAVs. So we need to keep track of these moving applications. And I will be discussing this framework in such a scenario, but the mathematical framework is more general and it can be applied to any parameter estimation framework. So assume we have a vehicle, say at time t equal to 0, and it is moving in a straight trajectory at time t, and the initial positions are represented as p, the velocity v, acceleration a, and as a third observer who is at some place away from the um, as a outside observer, the observer needs to measure these states, which are the position, velocity, and acceleration. And the trouble is that we cannot measure these states directly. So we need to take some measurements, which is possibly the range in this case, that is the distance between the observer and the um, vehicle. And so the idea of this entire framework is to measure the state through observations. These observations are represented as y, so y of t, and we have an entire set up to time t, y0, y1, and so on. And we want to estimate the x, which is p, v, and a at t plus 1 through the y's. And this process is referred to as filtering. So if we have a basic Newtonian mechanics, so the position at t is the initial position plus v times t. And if we so this the first equation is more with respect to constant acceleration, and if the acceleration is not constant, or if we want to measure the acceleration, we have a quadratic equation, nonlinear equation, quadratic in time. So we can have both these examples I have mentioned here, because one is linear in time when we want to only measure the velocity at constant acceleration, and the other is not linear in time. So it's non-linear in time. And in a very ideal scenario, when there is no noise, there is everything is good. So we have the ideal case, which is pt is p0 plus t times v0. But say there is an influence of noise. Now this noise, I'll call it as process noise. So the vehicle which is under motion, the velocity gets influenced by noise when the vehicle is in motion. And so say the v0 of t is now being influenced by this del of vt, which is the drift or the noise in velocity. And so this is the overall motion model. Now, the idea is to first develop the system dynamics. That is how if the motion is happening, how do we capture the motion mathematically? So we have pt, which is the previous pt plus t times vt, and the vt is the initial velocity plus del vt, which is the drift in velocity. And the drift in velocity is also not constant, but it is continuously evolving with time, right? So if we capture it in a matrix form, the states which need to be tracked are vt plus 1 and del vt plus 1. And so this is in a matrix form. Xt plus 1 is a times xt plus b times ut plus v, which is noise. U is the input or the parameter which we can observe. Uh, and so if you observe this entire system dynamics, this is a linear system dynamics, that is just linear in time. So this is an example of a linear time varying system. Let me take another example. So say in this case, we want to measure the acceleration in addition to the velocity. So similar as the previous one, we have the system dynamics, but the difference is that now the matrix AXT plus BUT is no longer linear, but it is now non-linear in time because there is a t square component which is involved. Right. Now, we cannot directly estimate the vector x, which is a state vector. And so we need to do some measurements being a outside observer. And the idea is that the measurements y is a function of x. So we now have a function of x, that is h, and it is being influenced by another noise, which is the measurement noise. So the first we discussed the motion model. Now we are discussing the measurement model. And the idea is that because we cannot estimate the state directly, we need to take some measurements, and this measurement is a function of the state. And possible measurements in this case, if you are the user and you want to measure the object, so it is a range, which is a function of the position of the object as well as the user's own position. So this is the measurement model. So the motivation behind this analysis is that we have a real physical system, x of t, which we don't know what it is, and we want to estimate it. We can't do that. So we observe the y's, which are the measurements, and we try to have a model of the real physical system in a discrete time sense. So we have the matrix A, B, and H, and we try to get YT hat, and we try to see how close the predicted measurement YT hat is to the real measurement YT. And this tuning is done through the gain, which is the Kalman gain. I'll come to this, what it is. And so we are trying to approximate the real physical system with a discrete modeling, right? And the matrix A and B are known, they may evolve with time. The matrix H is known, it evolves with time. And the state is x hat of t plus 1, which delays to x hat of t. So this is a rough overview. And the estimate at t plus 1 is basically, we will see this is the ATXT plus BUT, plus this is a correction term which depends on some KT and the difference of the outputs which we are measuring, right? So, and this is the correction term basically. So what are the assumptions which we have taken in this entire analysis, which we will be taking? So the first is that the noise are considered to be uncorrelated white noise. The noises are additive in nature. They can be assumed to have zero mean. Further, the noises can have Gaussian distributions with, say, some covariance Q and R respectively. The noises are uncorrelated with each other in all sense. So basically the autocorrelation is zero and the cross correlation is also zero. Further, xt is a Markov process. So idea is that the state at t only depends on the previous state, which is xt minus 1, and the input ut minus 1, and not on all the other states. And but it needs to be noted that yt is not Markov. So while xt is Markov, yt, the process yt is not Markov. And higher the samples which we have, that is the observation samples of y, the more better is our estimate of x. And when the system is a linear time varying system, that is the function of x and u is linear. That is A and B are linear, matrix A and B are linear. The function H is also linear, and the noises are Gaussian. In that case, we term this as the Kalman filtering problem. And it is assumed that we know the distribution, that the initial state distribution, that is x0, and that is also considered to be Gaussian, having some covariance p0. And we also know the distribution of the noise V and W, and all the three are Gaussian in this case. So this is called a Gauss-Markov model, and the linear time varying analysis is the Kalman filtering problem. So on an overview, so we start with the sample estimates up to t-1. And once we have the observations up to t-1, the first step is to get the state estimate x hat of t-1. This is the first step. And once we get the state estimate at t-1, we then need to make an intelligent guess of the state at t given t-1, which is called the a priori state. And once you obtain the a priori state, x hat of t given t-1, the next step is to predict the output yt hat. And the process up to this point can be done completely offline. There is no need for real-time processing. So so we have samples up to t-1. We can obtain up to yt hat. Now, if we get the new observation at t, which is yt, then we take the difference, which is the prediction error, and then we have a Kalman gain, which is a function of this prediction error, and we try to correct the a priori state, which is x hat of t given t-1, which was obtained previously. And once we correct it, and then we estimate the a posteriori state, which is x hat of t, through the corrections, right? So, and this process is a real-time process or an online process. So the Kalman filtering algorithm can be broken into two parts. One is the offline analysis, and another is the online analysis. And these three parts, so the state estimate at t-1, the a priori state, and the a posteriori state, are the three stages in which this analysis will be done. So let's first see from a probabilistic perspective what is going to happen. So now we have these three states, x hat of t-1, which is the previous time state. Then we have the a priori state estimate, and then the a posteriori state estimate. And say they have PDFs g of t-1, g of t given t-1, and gt at xt. So now we apply the Chapman-Kolmogorov equation. So through Chapman-Kolmogorov, we want to estimate the PDF or the a priori PDF gt given t-1. So there is a typo here. It's this guy is a priori, and so we want to. The idea is that we have this PDF of gt-1 at xt-1, and through this we see the transitions which are happening. This is a Markovian transitions which are happening. So probability of xt given xt-1 ut-1, we don't need the previous state transitions. And we through these two information which we have, we want to estimate gt given t-1, which is the a priori estimate. And this PDF, that is the a priori belief, is basically integrating minus infinity to infinity, the transition probability from xt-1 to xt times the prior, which is the gt-1. And so the idea is that this gt minus 1 is initially coming from the initial distribution assumption which we have, which is of the PDF of x0, the state x0, and we start from there, and we try to obtain the a priori belief. And this probability, or the transition probability, actually comes out to be the PDF of the noise uh, uh, xt minus the function at t minus 1. So the idea is that at t we the function xt minus 1 ut minus 1 is a deterministic value, and this is basically the PDF of noise, which is the process noise in this case. And so if we know because we have assumed to know the process noise, and we know the initial distribution at x0, we can obtain the a priori belief. And this is the belief propagation law. So how the states are propagating. Now the next step is, once we have obtained the belief propagation, the next step is, once we obtain yt, which is the new measurement, and now we want to update the a priori belief. That's the next step. And so gt of xt, and now this is f of w, which is the PDF of the measurement noise, which is the second noise which we have, and yt minus h of xt times the a priori belief. So the a priori belief gets multiplied here, and we obtain the PDF of the a posteriori belief. So this is the from probabilistic analysis how the Kalman filter algorithm works, and it works in a recursive way, and that's why it is also called recursive Bayesian estimation. Now, if we see from a optimal filtering problem, the same analysis. So we want to minimize the mean squared error. We want to minimize the mean squared error. That is the xt hat minus xt square and the expectation of this term. Right? And such that we are given these two, the motion and the measurement models. So the first step is to obtain, so if we take the expectation of xt, and we can omit b of u, because it is basically a deterministic value and without loss of generality. So what we observe is that expectation of xt is at minus 1 expectation of xt minus 1, and this expectation of xt minus 1 is x hat t minus 1, which was the first step. And this expectation of xt is basically x hat of t given t minus 1, which is the a priori. Right? This is the first stage. Similarly, on the measurement side, if we have yt is hx plus w, so if we take the expectation of the y, so y hat is ht times expectation of xt. So what we have is yt hat is ht times the a priori state estimate x hat of t given t minus 1. And this is the predicted output. And now we want to compare this predicted output yt hat with respect to the actual measured output, which is yt. So how do we do the state update? So let yt be the newly observed output. And now we have this relation, that is the a posteriori is a priori plus this correction, which is dependent on the yt minus yt hat. And so let's have two errors. We define two types of errors. One is the a posteriori error, which is small e, which is x hat t minus xt. And we have the a priori error, which is epsilon. And this is x hat t given t minus 1 minus xt. So let's have these two errors which are possible, right? One is the a posteriori error, another is the a priori error. And if you just see the goal is to minimize the expectation of the a posteriori error. So this is basically the a posteriori error, which is et square. Now, these two errors are actually related to each other. That is the a posteriori error and the a priori error. And how they are related with each other? So they are related to each other through the Kalman gain, which is K, right? Or the gain of correction. And what we observe is that as this Kalman gain increases, ET first, it will decrease up to certain point. And then as the Kalman gain keeps increasing, ET will again increase. So why this is happening is because as the Kalman gain increases, the measurement noise gets amplified. So the Kalman gain is directly influencing the measurement. Also, as the Kalman gain increases, the a priori error, that is epsilon, reduces. Right? So the idea is that we need to find the optimal Kalman gain such that ET can be minimized. And in this trade-off, this optimum gain is referred to as the Kalman gain, at which the mean square error can be minimized. So the original problem was to minimize the mean square error, which is ET. And so we just need to solve for this. And so this is directly I've written the result here. So what we observe is that the Kalman gain is a function of Pt given t minus 1. So remember that P0 was the initial covariance of the initial state. And Pt given t minus 1 is the expectation of the a priori error. H is the measurement function. And R is the measurement noise covariance. So this is the expression for Kalman gain. So if I summarize the discrete time Kalman filter, we have the state propagation and simultaneously we have the covariance propagation. So we have the state propagation given by these two equations, x hat t given t minus 1, which is the a priori state. And similarly, we have the initial predicted output. And then we have the a posteriori state after the Kalman correction. And this is the Kalman gain. And similarly, the covariance keeps also keeps updating with each step as shown. So far we analyze the system from a discrete time perspective, but this analysis, the discrete time analysis, does not tell the stability of the system. We do not know whether at a time infinity or at steady state, whether the covariance error will converge or it will diverge or what will happen. So we need to analyze the from a continuous time aspect with respect to the stability of the system. So we'll see what happens. So far in the discrete time case, we had a delay. So the xt plus 1 delayed to xt. But in a continuous time case, the difference equations are now replaced by differential equations. And the delay, that is the delay of the time unit, is now replaced by the integrator. Now, this change which is happening in the continuous time with respect to the discrete time is going to bring some modifications. So let's try to model the noise, the process noise and the measurement noise. So the process noise Vt, so this is Vt, and this process noise, which if goes through the continuous time Kalman filter, gets integrated while it was not being integrated previously. So that if you see at a discrete, if the subscript t refers to the discrete time variable, and this gets integrated from t minus del t to t, and if I so this is v bar times del t. So the process noise gets multiplied by this factor of del t, which is your the modification which happens in a continuous time analysis. Similarly, the measurement noise, on the other hand, is basically the average. It's the time average of the sampling interval. And similarly, the covariances or the noise covariances also are now either being divided by the time period, or they get multiplied with the time period. Also, if we see the differential equation, that is x dot, which is dx by dt. So this is approximately xt plus 1 minus xt by del t. So if we perform this some algebraic manipulations, what we observe is that xt plus 1, so so in a continuous time equation, it can be mapped to a discrete time equation such that the variable at is now I plus ft del t. And similarly, this is the process noise, which now gets multiplied with del t. So if we try to map the analogy between the discrete time case and the continuous time case, what is happening is that initially we had a matrix at, and now it is being modified to I plus some f times del t. ht remains the same. The measurement noise variance gets divided by the sampling time period. Similarly, qt, which is the process noise variance, it gets multiplied by del t, and so on. The only change will come in the covariance update, and the covariance update is given by the Riccati differential equations in the continuous time domain, which we'll be seeing. So to obtain the covariance propagation in the continuous time domain, so we had this equation for the discrete time case, and if we substitute A, P, and Q from these, so what we observe is that as del t tends to 0, we have this expression d by dt of p. And this differential equation is termed as the Riccati differential equation. And this is used to measure the stability of the system. And we'll see how it is used to measure the system stability. So algebraic Riccati equation. So the questions which we have is, does PT, which is the covariance of the initial state, does it evolve with time? How it evolves with time? Does it converge? If it converges, does it converge to 0, or it doesn't converge to 0? So let's assume that the Riccati equation converges. That is, dp by dt tends to 0 as t tends to infinity, or pt tends to p infinity. So what we observe is that at the steady state, the variables becomes, and for a scalar case, we have all our variables, algebraic variables. And if we solve the Riccati equations, which is a second order algebraic equation, p infinity comes out to be this expression. And this expression is the steady state error matrix. So far, this analysis was done assuming that the Riccati equation converges. But even if we don't assume the Riccati to converge and perform the transient state analysis, it also comes out to be the same expression. So idea is to observe how p varies with time and if it converges or it doesn't converge. So we can analyze this for two cases. So if f is 0, so if f is 0, that is basically at in discrete case is basically an identity matrix if f is 0. And in this case, you observe that p infinity is root rq by h. So r and q are the noise covariances, and h is the measurement function. And so this comes out to be marginally stable if f is 0. And if either of r or q are 0, in that case, p infinity is 0, assuming that h is greater than 0. If we take another case, that is, there is no process noise, that is, the process is ideal. In that case, p infinity comes out to be r by h square f plus root of f square. So in this case, we have two sub cases, that is, f can be greater than 0 or f can be less than 0. So p infinity for f greater than 0, it turns out to be an unstable system. And if f is less than 0, p infinity turns out to be 0, which is a stable system. So the idea of discussing the continuous time domain system was to see how we can analyze the linear time varying systems from a stability perspective. Now I will briefly give some overview of the non-linear time varying systems. So far the entire analysis was a linear time varying system. Now if we have a non-linear time varying system, that is now the function f is non-linear and h also is non-linear. So the first we'll see the linearized Kalman filter, which is a very simple extension of the Kalman filter. So the idea of the linearized Kalman filter is to linearize the nonlinear state equation around a nominal trajectory. So let's take the x to be some x star plus del x. And del x is now my deviation with respect to the actual trajectory. And we have x star, which is the nominal trajectory. And the idea is that, so x dot was this was the initial expression. And if I replace x with x star plus del x, what we observe is that the state equation can now be represented in this fashion, where now you have the Jacobian at x star. So basically the idea is that you linearize the originally non-linear function f by differentiating the function at x star, which is a deviation, which is at a deviation of del x from the original x. And if so, this x dot is now it can be represented in this fashion. So let's observe this term, which is del x dot. Let's just observe this term. So if we observe this term del x dot, which is the Jacobian at x star times del x plus the noise, so we see that this can be, so this becomes another sub-state equation, kind of. So del x dot can be mapped to x dot. This becomes ft, del x is x, and this is the noise, right? So the idea of the linearized Kalman filter is that rather than estimating each x, I am now estimating the del x at each time instant. And similarly, the measurement equation can also be linearized in the similar fashion. But the problem in this kind of linearization is that this technique depends on the size of delta x, which we have considered. And if the actual trajectory may actually deviate very heavily from the nominal trajectory if the system is very nonlinear. So then we have the extended Kalman filter. So in extended Kalman filter, the Jacobian is evaluated directly at the estimated state and not at the nominal state, which is x star. So there is no need to take any delta x. So you directly estimate the Jacobian at x hat. And the other modification in the extended Kalman filter is that the state propagation and update use the full nonlinear state equation and measurement equation. So earlier we were doing the estimate of each delta x hat, but now we need to do the entire x hat. And so this is a rough flowchart of the extended Kalman filter. So we have the initial conditions P naught, x0 hat, and y. And what we observe is that first we compute the Kalman gain, then we update the state estimate with the new measurement. We have the Jacobians of the measurement and of the motion. We have the Riccati equations, which computes the covariance noise update. And finally, we have the Kalman gain again. So this is it keeps happening recursively. And the discrete time Kalman filter could be done some partially offline, partially online. But the extended Kalman filter has to be done entirely real time. So it's a completely online algorithm. So these are the references. This was a very good lecture of Harry Asada in MIT OpenCourseWare, if someone is more interested to read these topics. So yeah, mercy. Any questions?
I may have some. If you go back maybe to the, I think slide, it was around the beginning where you started introducing the drift with respect to the velocity.
This
the previous one, yeah. So yeah, exactly. So here the PT that you want to estimate is from the perspective of an external object, right? So you estimate the to the movement of another object, right? From a third perspective.
Yes.
What about self-estimation? Is it possible with this framework? Because if you are inside the object itself that needs to be estimating its own velocity, so how does it work?
So idea is like, so I'm giving another example. So say you have a space aircraft, and the engine temperature inside the aircraft is extremely high, and so you cannot measure the temperature from inside the engine. So idea is that you measure the temperature outside the engine and you try to predict the temperature inside the engine, right? So it's that kind of analogy. So if you are not able to estimate a particular parameter directly, we try to estimate it through a function of that parameter. So that's the entire point. So this analysis can be applied anywhere in any of such cases where you are not able to. So it's kind of a hidden Markov model flavor, right? So idea is you can have any hidden Markov model flavor to this analysis, and it will fit in its.
Okay.
So yeah.
Thank you. So, thanks again.
Okay, thank you.
We can go.
Thank you very much, Ashutosh.
Yeah.
Thank you. I will stop the mics and I will give back the mics to the entrance. I will also stop the